Morning Year 10. We are going to go through some quantitative chemistry this morning. We're going to use some practice of our calculations and you're going to have some to have a go at, and then next lesson I'm going to give you a mastery booklet for you to work through as well. So straight on to the visualizer. We are going to start off with the relative formula mass. So hopefully you've understood the relative formula mass, which we did recently in the previous lesson. And let's start with a simple one. Let's start with NaOH, and we want to find sodium hydroxide, NaOH. We want to find the AR of it. So we have to remember that sodium hydroxide, because it's 1 Na, 1 O, 1 H, is literally going to be Na, O, and a little H. And we need to find their relative atomic masses to start off with, A subscript R. Using the periodic table, we're going to come across and find the Na, and we'll find that its relative atomic mass, the top number, is 23. The relative atomic mass for oxygen is 16, and the relative atomic mass for hydrogen is 1. So we can say we've got 23, 16, and 1. So my total molecular mass, Mr, is going to be 23 plus 16 plus 1, which is going to be 40. So this NaOH, this sodium hydroxide that we're looking at here, would have a relative molecular mass of 40. Let's do a slightly harder one, just as practice. So we'll do H2SO4. I wonder if you remember what acid H2SO4 is. It's got sulfur in it, so it is sulfuric acid. Now break those down into the atoms we have. We have 2 H's. We have an S. And we have 4 oxygen atoms in our chemical. Now obviously it doesn't really look like this. This is just schematically drawing it to have an idea of what it could look like. So let's look at our relative masses for each one. We'll go back to the periodic table to help us. So H's, back up here, number 1. Sulfur, over here, 32. And oxygen, 16. So we've got 1, 32, and 16. But it's not as simple as that, because we've got 2 lots of H's, we've got 1 lot of sulfur, and we've got 4 lots of oxygen. So our relative molecular mass is going to be 2 lots of 1 lot of 32. Don't really need to keep the 1 there, but we'll do it for argument's sake right now, and 4 lots of 16. Which, if we do our calculation, we're going to add them all together. So the relative molecular mass of sulfuric acid is going to be 98. Okay, so I have some questions for you to have a go at now. Okay, so the 4 questions I'd like to have a go at are number 1, HCl, so 1 part A, hydrochloric acid. Number 2, part B, NaCl. Part C, iron oxide, Fe2O3. And part D, NH4 brackets 2SO4. Remember that the 2 acts on the whole of the brackets of the NH4 there, and the 4 obviously of the H acts on the H only, and the 4 of the O acts on the O only. So pause the YouTube video here, have a go at those questions, and we'll go through the answers in a moment. Okay, so let's have a go at some answers then. So number 1 was HCl. If you go to your periodic table, again, you will find that H has a relative atomic mass of 1, and chlorine, Cl, has a relative atomic mass of 35.5. So we can say that HCl has a relative molecular mass of 36.5. Okay, second one, part B, NaCl. So Again, looking for sodium. Sodium over here has 23, and chlorine again, 35.5. So we can say that our relative molecular mass is going to be 23 plus 35.5, which will give us 58.5. Part C, a little bit harder, you've got to find iron. This time iron, you'll see, is in the centre. It's got a relative atomic mass of 56, and oxygen has a relative atomic mass of 16. So we can say I have got 2 lots of 56 plus 3 lots of 16, which will give me an overall answer of 160. And the final one, again, going back to periodic table, nitrogen has a relative atomic mass of 14, hydrogen 1, so that's our NH4, sulfur and oxygen, so sulfur is 32 and oxygen obviously is 16 because we've done that one just now. So our relative molecular mass is going to be 14 plus 4, which is our NH4 part, times by 2, because that's all multiplied by 2. So in fact, I'm going to put that around bigger brackets, plus my sulfur, which is going to be 32, plus 4 lots of 16. Now my calculations gave that as 132. So we've got 4 different answers. Hydrochloric acid, 36.5, sodium chloride, 58.5, iron oxide, 160, and NH4 brackets 2, SO4, 132. Okay, so moving on to topic 2, finding an empirical formula. So this time we want to be able to work out the empirical formula from some mass values, and we're basically using all of the information we know about conservation of mass. So here is my example question. I want to determine the empirical formula when 1.7 grams of hydrogen reacts with both 52.3 grams of oxygen and 26.2 grams of sulfur. Okay, so we're told what we know, we're told the question, so let's now think about, in fact, let's underline what we know. So 1.7 grams of hydrogen, we know 52.3 grams of oxygen and 26.2 grams of sulfur. So we've got 3 different elements that we're going to consider. So step 1 is to write down the different element symbols that we know. I'm going to write them in order. So I know I've got a H, I've got an O, and I've got an S, hydrogen, oxygen, and sulfur. Step 2 then is to write down the masses that were given in our calculation, in our question. So we know it's 1.7 of hydrogen, 52.3 grams of oxygen, and 26.2 grams of sulfur. Step 3 is to calculate our relative atomic mass. So we'll go back to our periodic table. Hydrogen, as we already know, is 1. Oxygen over here is 16, and sulfur 32. So 1, 16, and 32. So those are the relative atomic masses, hence why they don't have any units. Okay, step 4. Step 4, we've got to divide the mass by the relative atomic mass. So I'm going to do 1.7 divided by 1 gives me 1.7. I'm going to do 52.3, the mass, divided by the relative atomic mass, which is 16, which gives me 3.27. And I'm going to do 26.2 divided by 32, which is going to give me 0.82. 2. Okay, so in fact, considering the fact we've done some extra lessons, we now know that those are the moles, the number of moles that we have of these chemicals. But let's not worry too much about that right now. So let's go to step 5. We're going to divide all of them by the smallest to get the simplest ratio. Well, the smallest is going to be our 0.82 here because it's smaller than 1.7 and 3.27. So I'm going to do 1.7 divided by 0.82. I'm going to do 3.27 divided by 0.82. And I'm going to do 0.82 divided by 0.82. Well, I know that that one is 1. And if we do 3.27 divided by 0.82, we should find that that one is 3.99. So very nearly 4. In fact, let's use our squiggly lines here to say that's 4. And 1.7 divided by 0.82 is 2.07, which is very nearly 2. So that means that my ratio is 2 lots of hydrogen for every 4 lots of oxygen and 1 lot of sulfur. So let's go with the elements we have. So step 6 is to write down the empirical formula. So I could write it as H2O4S, but we know that as something slightly better. And if I rewrite it as something we know, then I've got H2SO4. So we've got sulfuric acid. Okay, so your 3 questions that I'd like to have a go at are to determine the empirical formula for, question A, 19.5 grams of carbon reacting with 22.8 grams of lithium and 77.9 grams of oxygen. B, 211.8 grams of oxygen reacting with 141.2 grams of sulfur and 247.1 grams of iron. And question C, 4.3 grams of nitrogen reacting with 14.7 grams of oxygen and 6.1 grams of calcium. So pause the YouTube video here and carry on once you're ready for the answers. Okay, so let's go through the answers then. So we'll go through each one. So question 2, part A, we want the empirical formula for 19.5 grams of carbon. So we're going to write down carbon reacting with 22.8 grams of lithium. So we'll write down lithium and 77.9 grams of oxygen. So we'll write down oxygen O. So let's write down what masses we know. So we've got 19.5 grams, we got 22.8 grams, and we got 77.9 grams. We need to know their relative atomic masses, so let's bring in the periodic table. So carbon is 12 over here, lithium over this side is 7, and oxygen, as we found out before, is 16. So we've got 12, 7, and 16. Okay, next step, step 4 in fact, is to divide the masses by their relative atomic masses. So it's going to be 19.5 divided by 12. That's going to be 22.8 divided by 7 and 77.9 divided by 16. If we do that on our calculators, we should find that 19.5 divided by 12 is going to give us an answer of 1.625. 22.8 divided by 7 is going to give us an answer of 3.25. And 77.9 divided by 16 is going to give us an answer of 4.87. Rounding it to 2 decimal places. Now we're going to divide by the smallest number. So I've got 1.625 divided by 1.625, which will give me 1. I've got 3.25 divided by 1.625, and I've got 4.87 divided by 1.625. So 3.25 divided by 1.625 is going to give me an answer of 2. And I've got 4.87 divided by 1.625, which is going to give me an answer of roughly 3, 2.99. Well, in fact, I'm going to say that that is 3. So I've got a 1 to 2 to 3. So looking at my empirical formula, I've got C, Li2O3. Well, we know that C and O normally go together, so therefore my answer should be Li2CO3, lithium carbonate, Li2CO3. So let's move on to part B. Let's have a go at that one. So this time I've got 211.8 grams of oxygen. So 211.8 grams of oxygen. 141.2 grams of sulfur, 141.2 grams of sulfur, and 247.1 grams of iron, so 247.1 grams of iron. We need those relative atomic masses. Iron is 56, sulfur we know is going to be 32, and oxygen is still remaining as 16. So I've got 211.8 divided by 16. I've got 141.2 divided by 32, and 247.1 divided by 56. Do those on our calculator. So 211.8 divided by 16 will give us an answer of 13.23. In fact, 13.24 if we want to be accurate. 141.2 divided by 32 will give us an answer of 4.41. And 247.1, divide that by 56, will give us an answer of 4.41. Okay, so we're going to divide by the smallest. So it's going to be 13.24. Divide that by 4.41. That's going to be 4.41 divided by 4.41. And that's going to be 4.41 divided by 4.41. Well, that's 1. That's 1. And that one, if we do it, 13.24, divide that by 4.41, will give us an answer of 3.00. So effectively 3. So we know we are O3 SFE. Doesn't look quite right, does it? Oh, let's move the visualizer down. O3SFE doesn't look quite so right, so that means we'll change it round. Always put the metal first. FeSO3 iron sulfate. And let's move on to the last one, so part C. Check we've got this one correct as well. So we've got nitrogen reacting with oxygen and calcium. So nitrogen reacting with oxygen and calcium. Nitrogen, I've got 4.3 grams. Oxygen, I've got 14.7 grams. Calcium, I've got 6.1 grams. I need to know their relative atomic masses. Nitrogen is 14, oxygen is 16, calcium's only one I don't know, 40, looking it up on the periodic table. So I've got 4.3 divided by 14, I've got 14.7 divided by 16, and I've got 6.1 divided by 40. If I do those three calculations, so I've got 4.3 divided by 14, which is going to give me an answer of 0.31. Got 14.7 divided by 16, which is going to give me an answer of 0.92. I've got 6.1 divided by 40, which is going to give me an answer of 0.15. So the smallest is the 0.15. So we're going to do 0.31, roughly 0.3, let's say, divided by 0.15. We're going to do 0.92 divided by 0.15. And we're going to do 0.15 divided by 0.15. Well, that one I know is 1. 0.31 divided by 0.15 is going to give me an answer of 2.06. So we can say effectively 2. And 0.92 divided by 0.15 is going to give me an answer of 6.13. I think we can approximate that one to 6. So I've got 2 lots of N and 6 lots of O. So I've got N2O6Ca. Ooh, not very nice to read, but that's a nice ratio, isn't it? So I could say I've got Ca NO3, which we know is a nitrate, 2. To be honest, if you got to Ca N2O6, I can't imagine you'd lose any marks. Obviously, this is the correct one because of the nitrate ion at the end. So we'll go for the third of our quantitative calculations that we need to be able to do. And in this one, we need to find the molecular formula, especially when we're given the empirical formula, and then we need to, and we're given its relative formula mass. And that will allow us to calculate the molecular formula. So let's have an example again. The empirical formula for octene is CH2 and its relative formula mass is 112 grams. Determine the molecular formula. Okay, so we need to work out molecular formula from what we know. 3 steps again to this one. So step 1, we need to find the empirical formula mass. So we need to find the MR of CH2. Well, using the periodic table, we'd know that C was 12 because we've done that multiple times today, and H is 2 times 1. So we'd have an MR of 14. We're then going to see how many lots of that 14 goes into the relative formula mass. So effectively part 2 of this is to divide the mass that we're given 112, divide that by the empirical formula mass, which will give us the scaling factor effectively, how many times we're going to have, because what we've got is we're saying I've got a C, an H, and an H, but I've got N lots of it, and how many N's am I going to have? So I've got 8 lots of those N's, so that means I end up with 8 lots of CH2, which is really C8H16. And there's your answer. So we're going to have a look at some questions now and make sure that you guys can do them. So 1 second, let's switch over to the PowerPoint. So 3 questions again. Determine the molecular formula for empirical formulas of CH2 and the formula mass being 60 grams, NH2 and the formula mass being 32 grams, and C5H11 and the formula mass being 142 grams. Pause the PowerPoint, pause the YouTube video here and have a go at these questions, and then when you're ready to carry on, you'll be able to see the answers that we're going through. Okay, so let's go through some answers. So question 1, we had the empirical formula. So part 3, part A. The empirical formula was CH2O, and we're told that the formula mass was 60 grams. So step 1, as we've done before, is to find the relative molecular mass of the empirical formula, CH2O. So that is going to be 12 plus 2 plus 16, which is going to give us an answer of 14, that's 20, so that's 30. Yep, 30. We're then going to do step 2. We're going to divide the mass we're given, which is 60, by our relative molecular mass, which is 30, which is going to give us 2. So our answer is going to be 2 lots of CH2O, which really is C2H4O2. So there's part A. We'll do part B on this side. So part B this time, we had NH2, and we knew we had 32 grams of it. So step 1, we want the MR of NH2. N, we know, is a value of 14. So we've got 14 plus 2, which is going to be 16. So step 2 is going to be 32 divided by 16, which is 2. It's always going to be a whole number, this one, so you never get a decimal here. And then step 3 is going to be 2 lots of NH2, which is going to give us N2H4. Hopefully these are relatively straightforward for you. On the page, do one more. So part C. Part C, we're given C5H11, and we know the formula mass is 142 grams. So step 1, let's work out the MR of C5H11. So that's going to be 5 lots of 12 plus 11. And 5 lots of 12, turn the calculator on, that'd be helpful, is going to be 60 plus 11, which is going to give us 71. Step 2, we're going to do 142 divided by 71. Oh look, we find that that's 2 again, which means that we've got step 3, 2 lots of C5H11, which means we've got C10H22. So well done if you've got all of those correct. That's absolutely fantastic. Okay, so on to part 4 of our quantitative chemistry recap. This is concentrations of solution. Remember that concentration of solution is all about taking a volume of water. So here's our water in our beaker, and then adding some mass to it and dissolving that mass inside of our water. Now, most important thing to remember is that volume is in decimeters cubed, and 1 decimeter cubed is equal to 1,000 centimeters cubed. Or we go the other way, 1 centimeter cubed is equal to 0.001 decimeter cubed. So we've got to make things smaller if we're in centimeters cubed. And in fact, to get from that one to that one, we are dividing by 1,000. Okay, so let's do an example for us to start. Or in fact, let's do the equation. So concentration is equal to the mass in grams divided by the volume in decimeters cubed. So let's do our example. Calculate the concentration, I'm going to cheat here, conc, excuse me, of 25 grams of HCl, hydrochloric acid, dissolved in 300 centimeters cubed of water. So there's our question. Okay, so first step, step 1, is to make sure that the liquid is in decimeters cubed. The volume must be in decimeters cubed. So step 1, we're going to do volume, and our volume at the moment is 300 centimeters cubed. That is less than 1,000 which is what we've said 1 decimeter cubed is. So remember that if this is my 1,000, what we're actually saying is we've got this much. Well, if that is 0 and that is 1,000, or that is 0 and that is 1, then that must be less than 1. So we're going to do 300, divide that by 1,000, which will give us 0.3 decimeters cubed. And then step 2 is to work out the concentration, which is going to be 25 because we're already in grams coming from up here. Divide that by 0.3, which will give us an answer of 83.3. Oops, can't see that, sorry. 83.3 grams per decimeter cubed, GDM to the -3. Don't worry too much about that. So that means that in order to get this concentration for 1,000 centimeters cubed, we'd need to dissolve 83.3 grams. If I wanted to get this concentration for 2,000 centimeters cubed, then I'd need to dissolve double this, so 166.6 grams per decimeter cubed. And if I wanted only 500 centimeters cubed, or 0.5 decimeters cubed, I need to half this, which is going to be 41.65, something like that, grams to dissolve in that amount. So this tells us effectively how much of the solid we need to dissolve to get that concentration. Okay, so it's going to be over to you, and you're going to have a go at some of these questions. So 3 questions and an extra question for you as well. Let's see if you can do the extra question, and maybe you could do the extra question before you start these 3 examples that I've given you. So name the acid and calculate their concentrations of 40 grams of H2SO4 in 200 centimeters cubed of water, 500 grams of HCl in 400 centimeters cubed of water, and 2 grams of HNO3 in 0.45 centimeters cubed of water. And your extra challenge is which has the highest concentration, if you can predict it beforehand, and was this a surprise? Are you surprised about which one has the highest concentration? So pause the YouTube video here and then have a go at these questions, and we'll go through the answers in a moment. Okay, so back to some of the answers that we want to go through here. So the first question said we had 40 grams of H2SO4 in 200 centimeters cubed of water. Now hopefully you realise that H2SO4 is sulfuric acid. So it's a good start. Hopefully you got that one correct. And if we want to work out our concentration, then we need to know the volume in dm cubed, which is going to be 200, divide that by 1000, which should give you 0.2 dm cubed. So the concentration is going to be the mass divided by the volume, which is going to be 40, divide that by 0.2, which should give you an answer of 200 grams per decimeter cubed. That's the first one. Quite a large concentration, that one, 200 grams per decimeter cubed. High concentration. Okay, part B. This time we've got 500 grams of HCl in 400 centimeters cubed of water. Well, HCl is hydrochloric acid. So hopefully you managed to remember that one. Our volume again is in centimeters cubed, so we need to deal with that. So volume is going to be 400, divide that by 1000, which is going to give us 0.4 dm cubed. So our concentration is going to be equal to mass. Always write your equation. Remember, you're trying to remember this for the exam. Mass divided by volume, which is going to give us 500, divide that by 0.4, which is 1250 grams per dm cubed. Sorry, couldn't see that one, but there you go, there's the answer. So concentration is mass divided by volume, 500 divided by 0.4, 0.4 coming from our decimeter cube volume here, leaving us 1,250 grams per decimeter cubed. And let's do C. This time we're told we've got 2 grams of HNO3, and it's going into 0.45 centimeters cubed of water. HNO3 is nitric acid. So hopefully you remember that one. So let's do our volume first. So volume is going to be 0.45. Divide that by 1,000. It's going to make that very, very small. So 0.45 divide that by 1,000 is going to be 4.5 times 10 to minus 4. What does that really mean? In fact, decimeter cubed. Well, that means I've got 0.45 and I've gone 1, 2, 3 spaces. And then I filled those with zeros, and that's where my 4,5 goes. Oh, ignore that for a second. With 0.45, I've gone 1, 2, 3 spaces. I'm going to go there, put the 0 there. 1, 2, so I've got 1, 2, 3, and then 4, 5. So it's 1, 2, 3, 4 to be in between it, which is minus 4. And then my concentration is going to be my mass divided by my volume, which is going to be 2 divide that by 4.5 times 10 to the minus 4. Remembering, in order to do that on your calculator, you're going to use that EXP button down here. So let's do the calculation together. So let me 2 divide that by 4.5, that times 10 to the x, or EXP button, depending on your calculator, minus 4. Remember, it's that minus, it's not that one, because that'll make you have an error. Press the equals and you'll get your answer, and it's going to be 4,444.4 reoccurring grams per decimeter cubed. So in fact, I would need nearly 4.5 kilos of this nitric acid molecule inside every 1 decimeter cubed to have this concentration. So which had the highest concentration? Well, the highest concentration was in fact C. Why was it a surprise? Well, it was a surprise because it had the lowest amount of mass going in, and what you probably would have thought was that the 500 one was going to have the highest concentration because you're putting the most mass in, but actually putting the most mass into the most water. Here you're putting the least mass out of all of them, but into a much smaller volume of water. Therefore, the concentration is higher. So we'll leave this here. Next lesson, we'll go through some of the mole calculations, and we'll make sure you can do those. Practice these questions. Really give them a go at practicing them. Look in the textbook and you'll find more examples of them. I will also upload a mastery sheet with this that you can work your way through and have a go at as well. Hopefully this has made a bit more sense. I know these quantitative ones are not the easiest to work with, but as always, send us an email if there's anything you can't do, and it's science at your school address. So I will end the YouTube video here. Hopefully that went nice and well for you, ladies and gentlemen. Like I say, let us know anything you can't do.